back to the lecture and look at. So we have seen many of these things. So I'm going further. I think I've stopped here with this image last time, and so let's continue at this point with some micro machining examples. And of course I'm making the distinction between bulk micro machining and surface micro machining. Surface micro machining you have already seen a beautiful example of, and so bulk micro machining means usually etching silicon of some silicon wafers, or under etching microstructures that are resting on silicon to release them to become mechanically mobile or thermally insulated or so. And there are different types, of course, isotropic and anisotropic etching. One can do it using dry chemical methods by gases reacting with silicon, or we can do it wet and solution. And here are some common systems. Wet solutions doing silicon etching include the HNA system. HNA is the abbreviation of hydrofluoric acid, nitric acid, the second compound, and acetic acid, Essigsäure in German. So Salpetersäure, Essigsäure, in English, hydrofluoric, nitric, and acetic, HNA. And so that etches isotropically. And by isotropic, for those who might not know, it could be, so if I have a silicon wafer like this with some protection layer, how will it be etched? So it will be etched in all directions with the same likelihood, which will produce a structure that will look like this. Actually, this should be rounder, semi or partially circular, so that the etch speed in all directions is similar, a bit like Huygens principle of optics, where optical waves propagate in all directions with the same likelihood, and so this would be called isotropic, as opposed to anisotropic, where the etching takes into account or is influenced rather by etch planes. And so maybe I should even be more precise. I should remove this first surface to say that it has been etched. And so here also there has been some etching, removing of material until which boundary? Until a boundary that might look like this. And so here we have these 1-1-1 planes. Of the 1-1-1 family. I put curly brackets around to say that these are equivalent to some, of the 1-1-1 planes, some examples, and this would be maybe a 1-0-0-1 plane, parallel to the 1-0-0 wafer. So that would be a 1-1-1-0 wafer of silicon that can be etched like this. And so anisotropic solution of silicon, such wet solutions are alkali, metal hydroxide, KOH, sodium hydroxide, potassium hydroxide, lithium hydroxide. They all exist. We can really go through the list. There is also ammonium hydroxide. So this has something to do with ammonia. TMAH, tetramethyl ammonium hydroxide. So this is tetramethyl, and the tetramethyl you see here, this the ill is probably here, this alcohol, and then here we have this tetramethane, and there is also ethylene diamine pyrocatechol, commonly abbreviated as EDP. So people only talk about EDP solutions. Those have been used a lot in my postdoctoral period because it has a wonderful advantage. You can etch silicon neatly, and it is selective to all the other materials of the CMOS process. So for instance, it doesn't attack the passivation, it doesn't attack the oxides, and most importantly, it doesn't attack the aluminum. So you could just put your pieces in EDP and then wait, and then the etching will occur, and then you can clean, and you have your microstructure. However, ethylene diamine pyrocaticol has a bad reputation now as potentially being a cancerogenic. So if you use it, you have to protect yourself, and you have, of course, the full protection, the facial mask, and the aprons, and the thick gloves, and then you know, flow hood, and they're clumsily etched now. Then there is also hydrazine, which is also not a healthy compound, which does something similar. And then you can also, and we will see examples of those etchings later. You can also do dry etching of silicon. The most convenient one to do dry etching of silicon is xenon difluoride. We have a machine here also in the clean room. Fluorine etches silicon very efficiently, and it forms this highly unstable compound with xenon. So that xenon is actually in a bottle as a solid, but under pressure, and then if that bottle in the vapor, with which the solid is in equilibrium, is allowed to escape from the bottle and flow over the silicon wafer, and there it will xenon difluoride will decompose, and the fluorine will much more readily react with the silicon than with the xenon, and then form some silicon fluoride compound that is then eliminated, and therefore we have some microstructuring. Or you do it with plasma support, plasma etching, so-called reactive ion etching, or deep reactive ion etching, for deeper distances, it can be used. So here are these two examples. Again, left you see isotropic, right, anisotropic etching. You see also a little bit of under etching. So this is the under etching. Where is it mentioned? So here we have under etching, and here we have a lot of under etching. So in principle, perfectly anisotropic etching will not produce an under etching, but in reality it does. Isotropic etching will always produce under etching. And the etch selectivity to thin films, for instance, these protecting films that we would like to use as structures beneficially, might be important. So selectivity means the ratio of the etch speed. If something is selective against, so a KOH or the silicon etching is selective against this top material, it means that there is a ratio of the etch speeds, micrometers per minute against nanometers per hour, that is high. Selectivity is then said to be high. So here you have some examples from a book which I also brought. Actually, this book is called Simons MEMS. It was produced by a friend of mine, and Zurich and Barthes formerly now in Dubai, and they asked some of their friends to write chapters for this book. However, my course is not a transcript of that book. It's more for additional inspiration. And so here you have these different solutions: HNA, KOH, TMAH, xenon difluoride, deep reactive ion etching, what they are: wet, wet, dry, dry, anisotropic, no, yes, yes, etc. What their etch speed is, for instance, the etch rate of silicon 100 is micrometers per minute. How many? Well, typically more than 3, 2.5. At what temperature? At this temperature. Does it etch silicon oxide? Nanometers per minute, so the selectivity is not so good. Here the selectivity is quite good, and so on. Many things that you can read here. Sometimes the selectivity number is given 1 against 3,600. So that's a high selectivity. Xenon difluoride is highly selective against silicon oxide. It etches silicon 10,000 more strongly than silicon oxide. So silicon oxide is a wonderful protection material. Yeah, the cost is low when you only have solutions. You need a beaker and a little, thermal, how do you call that? Now I forgot the name. There's the hot plate, yeah, and maybe a stirrer, maybe a combined hot plate stirrer, and then a holder for your silicon piece. So that's something very cheap. For xenon difluoride, you need a deep reactive ion etching, you need technical infrastructure because xenon difluoride is highly reactive and you should not release it from the system. So this needs, pumping and very good mechanical components. And deep reactive ion etching needs, of course, an ionization source for the gas that it uses. So that's a complicated machine that easily costs $1 million. And so the result of CMOS bulk compatible bulk micromachining are these structures that we have seen in cross section already a few times, but in 3D, of course, now you see them more plastically, one-on-one walls delimiting these inverted pyramids or truncated pyramids, Pyramiden, as it is called in German, truncated pyramid. The pyramid is cut at its top somehow, making it flat. Now that's an inverse pyramid, of course, and sometimes they can be real pyramids. Sometimes they are grooves with a bottom line. Sometimes they are cavities with a bottom surface. And sometimes they're etched really right across the wafer just to release something which is on the other side, a dielectric material. And so we have sometimes, for instance, boron dope membranes or p-dope membranes with lower boron concentration that can be left there by some electrochemical stuff, which is also neatly used. And if we apply that to CMOS compatible CMOS structures, what might be produced? So if we etch across the wafer from the back, we can stop at the first layer that is not silicon. What is the first layer that is not silicon? It is the field oxide. If we have designed that field oxide to be so large to receive that etchant, and if the etchant doesn't attack silicon oxide so much, if we stop fast enough, then that field oxide will be mostly intact, and everything that is on top will also be intact. And what do we have available? We have available other materials of the CMOS process, like polysilicon, other dielectric layers. We have metal 1, metal 2. We might have all kinds of other materials if the CMOS process is more complicated. And those can be designed into useful structures. Or we have here such a membrane of those many dielectric materials with its metal layers integrated, with some silicon hanging there. That's possible. If you make it happen that this silicon piece, this diffusion, an N diffusion in a P wafer has a potential, electrical potential, with respect to the solution, by applying a counter electrode and then this voltage source and then a contact to that red zone by the contact lines running over the wafer, then the etchant will etch the silicon, but it will spare this charged or electrically charged piece. It will stop at its boundary, at the boundary of the P-N junction. And then you have an active device because that N region might have some P diffusions, it might have transistors, and might have other diodes, NP diodes in there. And so you can do many things. You can heat it up, for instance, to make a chemical sensor, or you could just heat it up to have, I don't know, some heat source and make a flow sensor out of it, whatever. So this is the bulk silicon micromachining from the back. But you can also do it from the front. So let's think we open this oxide layer here from the field oxide to the passivation by photolithography and then etching, reactive ion etching through the yellowish part. We reach the silicon, and then we can use EDP or some other etchant hopefully that does not attack the aluminum. Otherwise, we have to protect the aluminum, and then we can etch into the silicon. And if the structure is well designed, it will even under etch that structure to release a free beam. And again, here that free beam can also host some of those electrochemically etched or remaining structures to do something else meaningful, to have some circuitry there, maybe a thermalized circuitry that does not change while the environmental temperature changes, to have something really accurate. And a really accurate voltage reference, for instance. But, it's a big design problem for circuit designers to have voltage references in CMOS technology. They should be independent of temperature, but they aren't. So maybe you can make the temperature constant and you have something else. So here you see examples of structures that actually were generated by me and my collaborators many years ago. Some beam structures, as you see here on the right-hand side, or a beam structure also with some additional arms doing something meaningful. They're not here only just to look beautiful. They're usually oxidic layers with a metal layer running along to feed here, for instance, a resistor, or here to feed another resistor via these two arms to heat up that structure, for instance, at this location, and then at this location to measure its temperature increase, and here at this location to measure the temperature of the chip, to know what the gradient is. And one already have a test structure for measuring the heat flow across thin materials, which means that you have a test structure for determining the material's thermal conductivity. So we were among the first to measure these properties of these thin films: thermal conductivity, Seebeck coefficient, thermal power, heat capacity, and all those things that are well known for macroscopic materials, but for thin films that are produced under various conditions that are not known, and basic principles, so you have to measure them. So we develop test structures to determine those properties, so that these properties can then be used in design software for producing sensors using those materials, flow sensors, gas sensors, what do I know, with trustworthy material data. This was a test structure to measure the absorption of sandwiches of materials, of CMOS materials, the absorption of infrared radiation for infrared radiation sandwiches. The structure on the left is kind of complicated. It's a cross with 4 arms that allow again to heat a resistor at each of the 4 arms, and then also to measure at the same time the temperature of those ends of the 4 arms. And such cross-shaped structures are well known in materials testing, in electrical materials measurements, as Van der Pauw test structure. I'm not sure you have heard that name. Van der Pauw is a guy who showed how to measure the sheet resistance of materials shaped arbitrarily with 4 contacts at their boundary, actually 4-point contacts. And the realization to approximate such point contacts is to make crosses with extended contacts that act as if they were point contacts, because they're far enough away from where the real action happens in the center. And so at one point, of course, I said, electrical conduction is very similar to thermal conduction. What can I do? A thermal Van der Pauw test structure. Just translating electrical potential gradients into temperature gradients, and electrical current flow into thermal current flow, heat flow, and then measuring temperatures instead of voltages, and measuring thermal current power. So this is the result, and it is suspended, so that heat can only flow in the plane of the structure. As in a conductor, heat can only flow in the plane of this thin conductor layer. And so we published that, of course, and actually we even won a prize at the ICMTS, the International Conference of Microelectronic Test Structures, many years ago. So they were quite enthused to see that one could translate this idea into the thermal domain. And now you may ask, why not having connected these cross ends straightforwardly, straightly to the walls of this cavity? Who knows that? What would have happened if we would have designed those arms straight? That's an important design of microstructures etched by anisotropic etching. Imagine that I had done that. What would be the top view of the exposed silicon? Something like this. So these are the windows. I could draw one of those windows here, some windows that are opened. So here we would have opened, and then we have these four arms, and then here in the center we have that cross structure. And so this is our intended big cavity. If I have my silicon exposed here, and here, and here, what happens? My anisotropic etching. Have you ever heard about anisotropic silicon etching? Four? Yeah. Yes. Yeah. So let's look at this one opening. We would etch a cavity of the shape, and then three others as well. We would have four separate cavities, and the part that we would like to have free is then still sitting on silicon. So, etc. Do you agree? Have you ever seen this anisotropic etching of silicon? No. I thought you had some lens. Sorry? And that is yes, that's what I asked. So the etchant goes vertically into that silicon material, but then there are these 1-on-1 walls that are not etched. And that means that we have these individual etch cavities, and if I waited longer, then of course that surface would recede more and more until at the end I have an inverted pyramid. And the way to let this etching do what it does to create this big cavity, we have to have these cavities overlap somehow. So that's why. So for instance, if I cut this here also, so like this, then what would happen? Trick 75B. Yes. So in such a scenario, there is no reason for this wall to be stable, because the etchant can attach at this corner here. It can under etch this structure, and then those two cavities will after a while join into a big cavity. And so this is what happens here. By these convex corners, well, I don't see the convex corner here so well in this color. So let me draw another color. This convex corner and this convex corner get under etched. This convex corner also gets under etched here as well. So what could look like a single cavity here is expanded at that corner into towards the cavity that could be considered a single cavity here. So those form a big cavity together. And the cavity that is formed here, is under etched to join the other cavity. And then after some while, everything becomes one big cavity. And that is exactly the point. You have to allow the etchant somehow to be on the edge. And convex corners are absolutely useful here. And the same happened here. Without those convex corners, if I had continued those structures to the other side, we would have had separate cavities here and here. And because we have these convex corners, it could under etch and make one big cavity over which these cantilevers are suspended. Yes. Yeah. Yes. Yeah. So you would have expected some etching like this, and then it's over. Game over. So there is a third dimension, in this structure. So I'm drawing the structure geometry, for instance, like this. Whoop, up. Okay. And now we have this. So here is there is also edge wall. So here we have now our convex corner. So the etching around the corner there, and then under the corner, and then it can slowly progress under the beam to release the whole beam until all the 1-on-1 walls are complete, and then it stops and we can only continue in this way. Is it okay? Okay. Good. Absolutely the same here. This wouldn't go also with only one pole or a line. It needs to go around some corner. And these are obviously cantilevers that were etched here. So what do we have here? We have some CMOS compatible anisotropic dry etching. Deep reactive ion etching, the so-called Bosch process. That was invented over 20 years ago by Franz Lermer, now an important guy at Bosch. When I was a student at ETH Zurich, Franz Lermer was a colleague of mine, a fellow student. So we totally lost track of each other, and then I first went into solar cell development, and then back to ETH Zurich. I didn't know about Franz Lermer, where he did his PhD studies. I think he did them in Munich, and I didn't know he was in Boston, and suddenly, people meet again. So expect to meet each other, maybe one or two of your fellow students again in some totally unexpected position. It's fun. So Franz Lermer and actually Angela Urban invented this process where silicon is attacked by, again, one of those fluoride-rich compound, sulfur hexafluoride, SF6, and then this is actually an isotropic etchant, pretty isotropic. Actually, it's not fully isotropic because there is also some magnetic field and RF power also. But it has an anisotropic component, and then after a short while, maybe after a few seconds, this is stopped, and another gas is introduced, namely C4F8, which you all know. You have it at home. Did you know you had C4F8? Okay. You may have Teflon on some hands. This is it. Okay. Highly resistant. Yeah? Good protection. And this Teflon layer forms now a protection everywhere. Yeah? And now comes again, after a while, the next SF6, which is able to break some of that Teflon and actually does so not only chemically, but by the directionality of the process. So the process is not fully isotropic. It has this anisotropic component. There is a physical action which removes that Teflon layer at the bottom, yeah, and does so less for the Teflon layer protection on the sidewall, yeah, and then the SF6 can produce the next level of cavity, yeah, which is then again protected, which is then again etched, which is protected, and so it goes down vertically if the etching protection parameters are correctly done, and you know, if you master the process, that's something which is you know, the technologists have to learn how to use a machine to produce vertical trenches, yeah? Holes, trenches. Yeah? And again, here is a process that has pretty good selectivity to oxide. So if this is an oxide mask, and it is 1 micron thick, you can etch 150 micron in depth before that silicon oxide mask is gone. And then there are some other aspects that technologists have to learn. So if you etch narrow holes or wide holes, so we have some protection layer up here, different. So this is the mask, and here we have the silicon. So this etching by the deep reactive ion etch process does not proceed with the same speed. So although you would say, oh, there is a little bit of difference depending on the geometry, and the width of the channels or the width of the holes is one aspect. If you're etching not holes but channels, the width of the channel is an aspect, and the difference of these etch depths that you achieve is called the loading effect. Loading effect. And if you imagine now that the wafer ends here and it has another protection of silicon oxide, and you continue to etch down step by step until you reach here. Unfortunately, it does not just stop, but it continues by etching sideways, because this oxide gets charged, and then etch species are redirected, and the vertical directionality is also a lateral directionality then, and then you don't end up nicely with clean walls. And apart from that, those walls are not flat anyway. So if I look at a wall, let's say here in detail, what will I see? I will see a structure that looks like this. So in 3D, kind of ripples that look like this, with the mask layer on top. So these are these structures. They're called scallops. They're called ripples. They're called all kinds of things depending on the person. So here's an example that was for the sensor that was used using deep reactive ion etching. It's a tactile instrument. By the way, tactile instrument where obviously the silicon chip was etched in a geometry again of a crossed bridge. So you can imagine these lines here to be trenches that go right through the chip. Okay, so from the top you have these edge-shaped openings that cut through the chip, and the piece that is in the middle, this from here to here and from here to here, this is kind of a cross bridge. Yeah, do you see that plastically in front of you? Mm. So, if I look at this from the top, yeah. So I draw the wafer, no, the chip from top. By the way, this was about 6 millimeters, so quite a large chip for a CMOS chip. Yeah, expensive area. Yeah, and so I'm imagining that I etch a structure like this. Yeah, so this is all removed, and this is also all removed. So the etch mask is on top, and it has it protects everything except the areas here where silicon is now exposed. And then I do my deep reactive ion etching. I do this removal of silicon right perpendicular to the chip structure. And at some point on the other side. Okay? So that is Schlitze. Eckige Schlitze. Okay? And what is in the middle is a cross chip. But that's not all. So if you now flip over the chip, you will see the same. So this side may be the CMOS side. Yeah. And then you flip it over, you have the back side. Yeah. And then you will see something which we did also. We also etched from the back. Deep reactive ion etching. And I'll draw that with a second color, yeah, blue. Yeah. In this form. Now that's from the back, like this, and of course here too, yeah, here too. Now, if I go right through the chip, of course, I have separate pieces that fall out of the wafer, yeah, because then there are some squares that pop out, yeah. So I do not etch entirely across the wafer. I stop at 10 micrometers or 20 micrometers before reaching the other side. This means that at these locations, yeah, if I again consider this to be the front, yeah, so I'm etching from the back in the blue regions and stop before reaching the front. That means that I have very thin silicon membranes there. Those membranes are flexible, whereas the pieces here have the full width. Here, 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 and here. They have the full width of the wafer. They are very rigid. So you can imagine this cross which consists of mechanical blocks, cubic mechanical or cuboid mechanical blocks connected to each other by thin silicon stripes, membranes that are flexible, like hinges. Hinge in German, and Scharnier. So this structure, this mechanical structure, can be mechanically deformed. I add this tip mounted here in the central hole that I can also etch in the first place right across the center. Yeah. So there's a hole, and then I attach this tip, and if I expose this tip to forces in the three directions, this will be able to somehow mechanically deform the cross bridge, whereas the remaining chip around is all solid and robust, and that means that there are then curvatures. For instance, if I load the structure from FZ, the Z direction, what will be the shape along this line AA? Yeah? A prime. Yeah? I will have the following shape. So at the beginning, A was flat. And let's say here is the membrane. Yeah. So I'm drawing the cross section along this area. I have solid silicon. Then I have here membrane. Then I have again solid silicon. I have again membrane. Yeah. Then I have again solid silicon, actually with a hole across. Okay, right through, and then the same story again. So can I draw this somehow? Yeah, careful enough. So, and our crossed membrane from here to here corresponds to from here to here. So from this location to this location, from this location to this location. Yeah. And now if I imagine to have this tip here with its little ball and I load it in this vertical direction, what will happen in maybe in orange? Yeah, this thing will be deformed. This thing will go up a little bit. Yeah. Then there is again a deformation. Then there is flat. Yeah. So flat, deformation, straight, deformation, and I can imagine now my block to be somehow, my God, it's not so easy to draw, so to be now deflected, in this direction, and thereby this structure to have moved out of the plane. And when I look at these membranes, so for instance, this zone here in magnification, so here is my membrane, with the silicon going down, and then after the deformation, this now is deformed to let this block, be deflected. And now here, of course, I have a stressed area. So if I implement a piezo resistor here, piezo resistor, which is a doped region in the substrate, and I contact that doped resistor by some metal lines, of course, with some additional yellowish insulation layers that you all know now. Then I have a way to measure that deformation. So I have a way to measure the force with which something acts on that tip. It's a vertical force sensor, so to speak. And the stronger the force, the stronger the deformation, the stronger the change of the resistance. So for those who don't know what a piezo resistor is, the resistance without mechanical force will change into a resistance with a change, and that change depends on that deformation or ultimately on the force of Z. And so measuring a resistor is nothing difficult. You apply voltage, you measure current, you apply current, measure voltage, and then you have your resistance, and you have your resistance change. And you can do that with many tricks like this and this. So this is one force, but if you imagine a horizontal force to be applied, then this cross bridge will deform differently, and you have other resistors at other places, and from the many responses of those many resistors, you can extract the three components of the force acting in the three directions. So this little tactile tool was actually implemented in a system by Zeiss. So in Oberkochen as a sensor in a big machine to actually measure the surface profiles of micro components. And the advantage of the sensor was that unlike the DECTAC or alpha steppers in the clean room, where you essentially measure vertical steps, with this instrument you can also contact from the side. So you can also measure steep walls very accurately, and then it gets flat, and then there's another steep wall, and you contact it from the side, and so you're able to accurately measure three-dimensional structures and small and three-dimensional microstructures. And the accuracy, according to Zeiss, is quite extraordinary because there's a lot of electromechanical systems around, but they claim to be able to measure these surface topographies with 10 nanometers of accuracy. That's good, Optical dyes can do that too, but they can't do it on the side. Yeah? They have the beam that comes from one direction. So let's look at CMOS KOH etching. As we implemented and it's still in production in some companies. Yeah, so imagine this wafer to have come out of the CMOS foundry with a slightly rough backside. It's not as rough as shown here. This is strongly exaggerated. There's the CMOS structures on the front, the circuitry, the interconnection lines, and so on. Yeah, so those are so actually there is a sensor passivation added on top, yeah, for stress compensation purposes that you'll understand in a while. Yeah, so that whenever we fabricated membranes, those membranes remain flat. And then an additional protection layer is deposited that can later be removed again. Yeah, so that the aluminum structures are protected against the etchant, the KOH. KOH aggressively etches aluminum. And so it wouldn't be good to leave that surface exposed to KOH. All the circuitry would be gone. Yeah. Then at the same time, this backside is polished to become flatter so that a mask layer can adhere better. Some silicon nitride, for instance, which is then structured so that silicon is exposed. And then these wafers are put into a special holder that protects the front again against the etchant that will surround the whole holder, and in particular attack this exposed surface to produce, well, this silicon structure progressively. So starting from here to here, and then continuing until all the silicon is gone, thereby reaching the silicon oxide on the other side, the field oxide. And because the front is protected, sealed from the solution by some seal rings, and then even cleaned with some rinsing liquid. So in case some KOH gets around the corners and leaks into this cavity, there is an additional protection so that really the front side survives. And once this is done, the wafer can be taken out. This protection layer can be wet etched, wet removed, and then we have a wafer that is finished. And I brought you one of those. Yeah. So here you have a 6-inch wafer, actually from many years ago. Yeah. But that was one of the successfully etched. So this is the front. Full CMOS. Recognize sensors that are by a stepper, probably exposing the machine that is based on the mass. Imagine that the concept that every one of those 25 or 30 control departments is right under the perspective. And then after this, the steps are out, and the result is now a structure with the back. And the fact that the really are is visible by looking across. Yeah. So only silicon oxide and the favorable aluminum constantly structure of the universe. Just like here, we also have some red, also some blue metal as a thermal couple, obviously, for a thermal sensor. Like the Lufer sensor or the Castor sensor. And so what you can do with the CMOS etching is, as you know, inverse truncated pyramids, rectangular grooves, membranes made of silicon if you don't etch through, or of dielectric sandwiches if you go right across, maybe with an etch stop defined by, well, of course, by the etchant selectivity, which is okay with the KOH. you kind of integrated structures in those membranes based on monocrystalline silicon. If you have membranes or polysilicon or metal, you can implement heating resistors. Using the gate poly or capacitor poly, you can make thermal elements, as you will see in the thermal thermal sensors, temperature sensitive resistors. Polysilicon is a beautiful temperature dependent resistor, so you can use it as a temperature sensing element. Piezo resistors, poly is also okay. It's not fantastic, but you could do that. But if you have silicon left, then you have crystalline silicon available for piezo resistors. And so here is an example, very early, actually. This will always be a historical date for me, because this was when this first integrated gas flow sensor system was presented by my student Felix Meyer to the International Electron Devices meeting of IEEE in Washington, DC. And the sensor part is right here in the center. This is about the size of the membrane, now viewed from the top. And then this contains thermocouples from two sides to measure two temperatures on the membrane. And it contains a line that you also see here that is a heater that allows to heat the membrane. And so when gas flow goes over that membrane, the heat dissipated in the membrane, heating the membrane, is carried by the gas to one side and makes one side, let's say the top side of the flow control, a little bit hotter than the lower side. And this temperature difference reflects the current, the flow of the gas over the membrane. It's a thermal gas flow sensor. And this design has a long history, because based on the success of IEEM, where Felix Meyer actually won the Best Student Paper Award, he and the colleague decided to think that that's a good idea. This can be as good as box, as the sensors of anywhere. How far away, and so they started designing these sensors and founding the company Sensirion, and a good share of products of Sensirion is now based on this type of sensors, of course, highly more elaborate. For instance, the packaging was kind of strange at that time. So we had, you see again this goldish color. Now you have seen gold before in this lecture. So you immediately know, this was produced at Microelectronic Maha with this gold bonding option. We put a seal ring of gold around the structure so that Felix could mount a counterplate with a hole so that the sensor would be, the rest of the circuit would be protected against gas, and the gas is then channeled only over the sensor area. And the contacting of the electric contact is also easier by the gold bond pads over there. And when you go to the website of Sensirion, you will see many liquid gas flow sensors, liquid flow sensors, gas flow sensors, flow controllers, mass flow controllers, differential pressure sensors. They're always based on these structures. What else shall I say? During the Corona pandemic, the gas flow sensor business at Sensirion expanded hugely because everyone wanted breathing. And those breathing, artificial ventilation of human lungs is a delicate thing. The lungs are delicate. And so you need to know how much gas you push into that lung for the person to be able to expire it later. Totally unnatural. Usually gas is sucked into the lung instead of being pushed into the lung. So this has to be done, with sensitive and trustworthy sensors, and that's where they want a lot of trust. So this make a big peak in their Umsatz. Yeah, I don't know how to say Umsatz in English. Revenue. Thank you. Yes, during 2020 and into 2021. Okay. Okay, so let me address two aspects here of this etching that is shows you that cross sections are easily drawn, but then the devil is in the details. So, for instance, CMOS wafers are highly imperfect. Yeah, so this is a cross section across a wafer, and you might think, what are these black things? Yeah. So these are defects that have been highlighted on this cross-section by some specific etching. These defects are there because the wafer is charged with oxygen. The wafer being pulled out of some recipient from the liquid melt, in this usually metal oxide recipient at 1,400 or some degrees. This melt is full of oxygen because of the oxygen in the container. And so this oxygen ends up in the wafer. And having wafers without oxygen is possible, but they are more expensive. So what do people do? They go through a temperature cycle, which I haven't mentioned so far, a pre-treatment, which allows that oxygen to aggregate into oxygen precipitates, little particles of silicon oxide buried in the wafer. At the surface, the oxygen is expelled by diffusion by the solution of the equation we have looked at today, because of a boundary condition saying there is no oxygen outside, so please diffuse out. And then there is this region, the so-called denuded zone, with little oxygen, in which the silicon is purer, and therefore a circuit can be filled. But inside it's dirty. And these precipitates, these little particles, influence the etching. Because when you think that a 1-1-1 wall is stable, this rests on the idea that this is a perfect 1-1-1 wall of silicon. But if there are little chunks of silicon oxide hanging out, then of course they can be etched all around and under etched, and then it goes faster. And then there is an etch rate of the 1-1-1 that is much faster than in a perfect crystal. And this has to be understood. And so we have developed, or we have helped the company identify a process that is still working for the CMOS, but is less hard on the material here, so that the under etching of the structures is lower, is smaller. This is documented here, that where actually there are the standard thermal treatment. The under etch rate per hour is 8 micrometers per hour, and without the thermal treatment, or with the modified thermal treatment, can be much lower. So that was a first thing. And then also we have removed backside, at the backside, silicon at the backside, in order to make it flatter, so that the rear protection layer that is needed for defining the membranes adheres better. And so we have analyzed the root mean square roughness of the rear side in angstrom, and then you saw how with that polishing process the backside became smoother and smoother. The second challenge was the mechanical stress. So here is a picture of a membrane with thermal pipes from both sides and a heater, so it could be also a thermal flow sensor. And from the color alone, you see that it's not flat. It is bulging out of the wafer. So the same thing that you have seen with the beams superficially under etched that have a pre-strain the bulk out of the plane, it happens also with the membrane. The membrane wants to be released, on the silicon. It is stuck, it cannot do anything, but as soon as the silicon is gone, it does what it can to release its strength somehow. But if that release is too strong, there is too much curvature, and then it makes not only it makes like a fling, and the membrane is gone. And so keeping that membrane flat or as flat as possible is the goal. And you do that by covering the membrane with silicon nitride passivation that has a cooling, a tensile strength. That makes like a drum, that wants to be flat. We put an additional drum layer to pull this flat, and the stress of this drum layer is documented here. So this says actually megapascal. So it is something which is in megapascal, and then there are different kinds of silicon nitride that can be deposited in a machine with one parameter called the low frequency power. And you see that you can reach layers from 300 megapascal to 0 megapascal. This means tensile, strongly tensile. Tensile means pull, and if we continued here, we would go into compressive, but we don't want compressive anyway. But so here it's clear that under these conditions, we obtain strongly tensile layers. And if we deposit that layer on top of such a membrane, then the average stress of the membrane is brought from this initial value to slightly negative to slightly tensile. And then if we take one of those less tensile passivation layers and deposit them, then well, we go less into the tensile region. And so now we can look at the bulging of those different membranes produced by these 8 combinations of 1 micron and 2 micron nitride on top of these oxide of that CMOS structure. And then you see that at least for the 30%, we got with 1 or with 2 micron nitride, we got a flat layer, a flat membrane. 40% LF power, 40% LF power, let's make that green, 40% LF power, so this and this 1 and 2 micron thick compensation. Well, in the case of 1 micron compensation, did not make the membrane flat, but with 2 micron it did. The 50 did it also. With the 60, no matter how thick, 1 or 2 micron thick, we could not make the membrane flat. So one of those parameters was then selected, and the membranes were reproducibly and reliably produced. And when you look at the wafer that I gave you, those membranes are there. So we're probably one of those successful layers. So it's quarter to 4, so time to stop. And therefore I will stop here and thank you for your attention, and then we can continue next Monday with the remaining exercise number 5. We will not be here, unfortunately, but we will do some exercise on and then I may also add 1 or 2 additional exercises. And then, as I discussed, it would be good, or I will show you or indicate you how to upload your solutions so that I have them available on the computer in case you would like to demonstrate something. So thanks you anyway for sending them already separately, but the next time we will be able to upload them like everyone else. Yes. Yeah, with that, I thank you, and I'm looking forward to next time.